Okay, this is video 3 of Unit 5 for Respiratory Therapy Science 2. We're starting in the PowerPoint section that is titled Detection of a Venous Sample. If you watch the video embedded within the PowerPoint, that's great. Otherwise, I did make another link to it in the content section under Unit 5. So either way, you should have watched the arterial blood gas video. So detecting a venous sample, you want to be cautious if your blood gas does not match your patient's condition. So if you get a saturation of 70 to 75% on your blood gas readout, a PaO2 in the 40s, and the patient just didn't seem like that should be reasonable, you can go check the patient with a pulse oximeter and then compare that saturation on the pulse oximeter to the one on the blood gas because you may have a venous sample. Analyzing the arterial blood gas, every hospital has at least one blood gas analyzer, and it's often kept in the respiratory care department where practitioners are responsible for performing blood gas analysis. If not, the analyzer then will be found in the clinical laboratory. A standard blood gas analyzer is unable to measure carboxyhemoglobin. You need a co-oximeter in the blood gas machine to measure the level of carboxyhemoglobin, which is the amount of carbon monoxide in the blood. The new machine, such as the ABL machine, does have a coax built right into it. Point of care testing. Point of care takes blood sample or blood gas analysis from a specialized laboratory to the patient's bedside. So this is just kind of like a portable machine. It gives a quicker diagnosis and treatment. The devices are very portable and small. And the blood going into these analyzers should not be chilled and should be run within 1 to 2 minutes after being obtained. So if you're using a point of care testing system, University of Iowa uses one, I know for sure, you do not chill those blood gases. They cannot be chilled, and you're also going to run them fairly quickly, so there's really no reason to have to chill those blood gases. Quality control does need to be done on the blood gas machine, and you can kind of follow that little chart there, but they're just doing it to make sure that the blood gas machine is calibrated and then that there's good record keeping being done on the calibration of those machines. Some other quality control things, record keeping, meticulous record keeping, and clearly written policies and procedures are the hallmark of a quality control program. So your hospitals that have blood gas machines in them, they will keep records on the analyzation of those blood gas machines, and they will also make sure that those blood gas machines are being calibrated regularly. Performance validation, process of testing a new instrument to confirm accurate measurement. It involves using samples of known values to assess accuracy. Preventative maintenance checks out different components, so filters, membranes, solutions, cartridges. They all have a limited life and deteriorate over time. Therefore, scheduled preventative maintenance should occur on blood gas machines. Automated calibration, blood gas analyzers regularly calibrate themselves, and the things that they calibrate are the oxygen electrode, the carbon dioxide electrode, and the pH electrode. This is a schematic quality control example. So the blue circles represent values outside of the standard deviation. So for the blood gas values for this machine, they all needed to fall within that standard deviation. And again, the blue ones are outside of control. So the blue dots on there are not within control for that blood gas machine. Those last few slides may not have been in your PowerPoints that were in your mod. I did make copies of them that I was going to hand out in class, but you should be able to just download them off of the Brightspace Unit 5 under the PowerPoints. They are in there if you wanted those to add to your mods. All right, the different electrodes that they're going to analyze. The first one, the pH electrode, is going to be referred to as what's called the SANS electrode. The PaCO2 electrode is called the Severinghaus electrode, and the PaO2 electrode is called the Clark electrode. All right, a little bit more about carbon monoxide. Carbon monoxide poisoning is the only commonly seen clinical situation in which a calculated saturation can be incorrectly high, which means that if you put a pulse oximeter on someone that has carbon monoxide poisoning, you're going to get a very high reading, but it's just reading the saturation of the hemoglobin. It's not reading what the hemoglobin is saturated with. So if the carbon monoxide is on the hemoglobin, your pulse oximeter is going to read 99 to 100%. If carbon monoxide poison is suspected or known, the patient's blood gas sample or blood sample should be analyzed using what's called a co-oximeter unit. You may also hear it referred to as a hemoximeter. So those are two interchangeable words, co-oximeter and hemoximeter. The newer portable pulse co-oximeter uses the same principle as our regular pulse oximeter. However, it does look for carbon monoxide. And those are usually red, but just know that some pulse oximeters are red too. So just being red doesn't mean that it's automatically a co-oximeter. A pulse oximeter unit also should not be used to measure SpO2 in those patients with carbon monoxide poisoning. Currently available oximeters are only able to evaluate functional hemoglobin. The non-functional carboxyhemoglobin will be ignored and the clinician will be given a saturation value for only the remaining functional oxyhemoglobin. So again, this is not going to give you an accurate reading on a pulse oximeter. Just some more on calibration and quality control. Calibration verification establishes and periodically confirms the validity of the blood gas analyzers. It does require analysis of at least 3 materials with known values spanning the range of values expected from clinical samples. So they'll look at generally the pH, the PaCO2, and the oxygen. At least 2 levels of control media should be analyzed during every 8-hour shift, and the rotation among the 3 levels should ensure that all 3 levels, again, your pH, CO2, and oxygen, are analyzed at least every 24 hours. And this is just another schematic of calibration and quality control looking at standard deviations. So the internal quality control takes it a step further by applying statistical and rule-based procedures to help detect, respond to incorrect instrument error. In one common method, the results of control media analysis are plotted on a graph and compared with statistically derived limits, usually plus or minus 2 standard deviations. So the control results that fall outside these limits indicate analytical error. So if all of the dots fall within those plus 2 and minus 2 standard deviations, then it's the blood gas machine is in control. I would just make sure that you kind of understand that the boards do tend to put a graph similar to the one that I have on this blood gas or on this quality control slide. They'll put a plus 2 and minus 2 standard deviation, and then they will plot data. And as long as the data all falls within the plus 2 and the minus 2, and there's no dots outside of that, that means that the sample is in control. Suspicious results, you can rerun the calibration for any of the electrodes and reanalyze the sample if you're suspicious of the results that you're getting. If the electrode will not calibrate close to the reference buffer solutions or gases, then that analyzer cannot be used. Blood gas manipulation. Arterial samples are used because the values reflect the patient's total cardiopulmonary status. Blood gas measurements are ordered to obtain, or to determine whether to change current therapy or to maintain it. So especially if a patient's on a ventilator, we'll run a blood gas machine to see if the patient's pH, PaCO2, and PaO2 are all within at least somewhat normal limits. Otherwise, we can manipulate that ventilator to hopefully change their blood gases. All right, so the next few slides are just a review on interpreting the blood gas. So I would advise you to pause the video after each change of the slide to make sure that you analyze it, and then I will give you the answer after you interpret them. So the first one, we have a pH of 7.57, a PaO2 of 25.4, a PaO2 of 98 torr, and a bicarb of 25 milliequivalents per liter. So go ahead and interpret that blood gas. Again, I would just pause the video so that you can do that and hear the answer when you get back on. So this blood gas is an uncompensated respiratory alkalosis. The PaCO2 is low, which is causing your pH to be a little bit high. So for this patient, if they were on a ventilator, I would suggest either decreasing their respiratory rate or decreasing their tidal volume to try to bring that PaCO2 and pH back into normal levels. The next blood gas, we have a patient with a pH of 7.45, a PaCO2 of 35 torr, a PaO2 of 53 torr, a bicarb of 26 milliequivalents per liter, and this patient is on 60% oxygen. So interpret that blood gas. This is a normal blood gas, and that patient has moderate hypoxemia. So since they're already on 60% oxygen, if they're on a mechanical ventilator, I would probably at this time start to add some PEEP. If they're not on mechanical ventilation, I would think about some sort of positive pressure. So either a CPAP, or more commonly, the patient would be put on a BiPAP machine. The next blood gas, a pH of 7.38, a PaCO2 of 61 torr, a PaO2 of 54 torr, and a bicarb of 33 milliequivalents per liter. So interpret this blood gas. This is a compensated respiratory acidosis with moderate hypoxemia. So this would be typical of a patient with COPD. So this patient would need no further treatment. Their pH is within normal levels, so that CO2 value for them is probably a normal value. The next blood gas, we have a pH of 7.29, a PaCO2 of 43 torr, a PaO2 of 87 torr, and a bicarb of 16 milliequivalents per liter. So go ahead and interpret that blood gas. This blood gas is an uncompensated metabolic acidosis. Next blood gas, we have a pH of 7.20, a PaCO2 of 22 torr, a PaO2 of 83 torr, and a bicarb of 15 milliequivalents per liter. Interpret this blood gas. This blood gas is a partially compensated metabolic acidosis. The last blood gas has a pH of 7.25, a PaCO2 of 65 torr, a PaO2 of 85 torr, and a bicarb of 33 milliequivalents per liter. Go ahead and interpret that blood gas. This one is a partially compensated respiratory acidosis. If this patient was on a mechanical ventilator, I would increase the respiratory rate or the tidal volume to try to blow off more of that CO2. All right, so this is the end of our arterial blood gas unit. Again, I will post the quiz on Monday, March 23rd, and that will be due Wednesday, March 25th. I will post the exam on Wednesday, March 25th, and that will be due Monday, March 30th. So you have some flexibility on when you can take those exams. Again, make sure that you email me or post your questions in the discussion area on Brightspace if you have any questions, either with the calendar or anything that we talked about in this arterial blood gas unit. Hopefully when we get back to school, we can get into the lab, we can practice blood gas draws, and then we can comp out on those on our artificial arm that we have in the lab. Again, if you have any questions, reach out. Otherwise, I will be done with Unit 5 here. And go on Brightspace and find all the resources. If you need anything, just let me know. Thanks.